I'll make up for what I missed last time. So I actually, if I'd have thought of this sooner, I might have asked you guys to wire up at least the clamp circuit, and you get the rectifier itself. You may not realize that you're seeing the diode drop. Now with the rectifier, you can measure V in and V out without hurting it. So your V out is here, and your V in is up here. And you notice that the peaks don't go all the way up to the whatever input you have. So in our case, I think it's about 10 volts, these transformers. They're about 20 volts peak to peak. Well, at least, let me take that back. I know the one, no, if it says 6.3, that's RMS, then the peak to peak is about 20 volts. Now, you really see it here in the clamp, and it's a bit counterintuitive. So notice that here it cuts off at 9.4. And he doesn't mark it here, but this one goes up to 10 volts. But notice that, well, no, wait a minute, it can't, because if, can it? No, yes it can, never mind. And you notice that it's down here that it looks different. Because if I measure, it's always 0 here. So it's no problem when you imagine that this guy swings up, and the positive way, the resistance here is 0, basically. So you're seeing basically the full voltage of the function generator. When it becomes so-called reverse biased, when you've got into here the negative lobe of the incoming sine wave, then the current flow is up this way. And if it's 0 here, then that means that I have to respect the diode drop, and so it's negative 0.6. It doesn't seem to make sense, but it just because then up here is the negative 10 at this moment. But we don't see that on the output. We just see what drops across that diode. And it's entirely consistent with our the voltage divider made of resistors, except that the diode is not ohmic. It just has a fixed drop. And where does that come from? I have a sketch I made on the front board there for Gyra, but I'll redo it here. And you can find in your book the same diagram. So first of all, to make a diode, is they put together two pieces of say germanium. In this case, could be silicon, the so-called semiconductors. And what they do is it's called doping. They dope this one. So let's say that you're in a vacuum chamber, and you place your piece of germanium, and then down below here, let's say you have a little cook pot, and then you have a coil, and you have some arsenic in here, and you heat it up, and they go every which way, and they penetrate into that piece of germanium. So if you look at energy levels, so in a conductor you have a sea of electrons. So it's one of those things about metals that when the metal atoms form a crystal lattice, it allows electrons to flow around, and then you have a net zero charge, but the electrons are allowed to roam around because of the existence of the crystal lattice. So, so there's a single so-called conduction band. You put a delta V, you have a hunk of wire, and you put a delta V, and you get current flow because there's lots of available electrons. Now, I'm going to hand wave at this, but in a semiconductor, you know about, maybe from quantum mechanics, you remember about energy levels of a hydrogen atom, n equals 0, 1, 2, 3. If anybody, does that sound familiar to everybody? Right? So you know that electrons can jump from, even in physics 2200, you learn a little bit about electrons jumping levels and emitting photons, right? So when it comes to and when you look at those light tubes, those are elemental gases, and they have simplistic energy levels, and so you can calculate. In a semiconductor, you have many atoms, and there's an interaction. So what you do, instead of having discrete levels, you have what's called energy bands. And I really need to take the time to go back and study this, and so I could explain it better. And what the doping does, it shifts the energy bands like so. So this is the doped half. And so when you put a delta V across them, you start pushing these guys up until they match. And then you can have conductivity. And that's not a very satisfying, this is the mathematical description. What you see in the outside world, if I make a graph like this, I and voltage, what I see in the outside world is that when I'm applying a negative voltage, I don't see any current in the diode. Now, and this is called reverse biasing. We need these words for understanding transistors. And this is the forward bias. And the bias is just, there's a delta V. Now, because of this energy band, it isn't strictly speaking a one-way valve. Well, even one-way valves in plumbing need a little force to open up the valve, right? If they're sort of spring-loaded. And that's basically what happens. As you cross over to forward biasing, that's when you're starting to push these energy bands up. And then you don't get full conduction, and then it basically goes to infinity. It's an infinite slope. And this is where your 0.6 is. So you start getting conductivity when these things start to overlap. And then when they fully overlap, you get all the current you want. And now there's no longer, you can't increase the biasing anymore. So the energy bands line up, and then they just stay where they are. Arsenic is a common dopant. And a slab of germanium. Okay. Oh, and of course you need another wire here. And then this is so after you do the half wave rectifier, then you move on to the full wave rectifier. And here is just a couple notes that you see 6.30 and 6.3, and you have your transformer here. And a transformer is basically two coils of wire, and they're actually wrapped around each other. If you go to my YouTube channel, I made this. I took my CAD program, and we should take a look at it right now. Of course I can't. There it is. Yeah, so let's take a look at this one. So I actually I modeled a transformer. So now you can see them lying around, and there's a metal frame here, and the metal frame is steering the magnetic flux lines. And one thing you'll notice is that let's see, I might as well skip this forward. Oh, it's coming really soon. That you see the lines inscribed in it. These things are made of layers of metal, and they're painted with a clear lacquer, and you don't want any conductivity across them because then currents can come. It's called eddy currents, and you don't want those. I'll talk about that more another time. The most important thing is that you end up, once they make this form, then there's two coils they're one on top of the other. There's some dielectric, and there's a coil, another dielectric, another coil, and then some inner dielectric, so that it insulates the coils from shorting out on each other and the metal form. It turns out transformers wear out because there's this AC voltage in there creating these varying magnetic fields, and the coils move a little bit and they rub against things and eventually short out, and then they get hot. And that's why you look at old radios and they smell a little bit, because the transformers are beginning to wear out. And it's burning. There's PCBs. The dielectric is basically paper soaked in this oily stuff. And back in the day was PCBs, but now we know they cause cancer, so we don't use them anymore. But many power stations still have liquid PCBs inside. When there's those substations with all the skull and crossbones, there's switches, and the switches operate in an oil bath. So, sometimes you can see an arc across the switch, and so they run it inside the oil bath. So basically, this is a 4-terminal transformer. We just happen to have a 5-terminal one. And so one coil takes and they're called step ups or step downs. Sometimes they're 1-to-1 to isolate. If you want to isolate yourself from the ground, you use an isolation transformer. That happens in audio stuff, and this is about the rest of the construction. So we'll stop this for now. So you have the two coils, and in this case, we do a center tap. So if you took your voltmeter, you would measure from 0, you could measure 6.3 RMS, or 6.3 RMS, or 12.6 RMS, depending on how you measure it. And this is also done in your house. You get two 120s. So if you needed 240 for your dryer or your electric stove, they use both of the hot leads. And in your house, the center one is connected to ground, but not ours. So anyways, we connect up our 6.3, and we notice we have head to tail, head to tail, tail to tail, and head to head. And if you think about it, you have a sine wave here coming in. So the flow here is constantly reversing. So if I'm flowing this way, then I go out, there's my positive. And, well, let's just go through the whole thing. Then I come back, and then I flow back to the transformer. If the negative lobe is now there, then the flow is backwards this way, right? But then you see, oh, then it's going in down here. And once again, the positive makes it that's why it's head to head. That's the positive side. And now the blue is doing exactly the same as the red until it re-enters, and now it comes back this way. And this is why, too, you don't want to ground. Well, obviously, you don't want to ground this end because you know that's your output. But if you ground this end, then depending on which way the sine wave is going, you have a potential with respect to ground. And one of these two guys is going to be forward biased, and it's going to burn up. And then the other one is, and then it swings the other way, then you burn up the other one. So they don't die instantly together, but they die. So you can't measure V in and V out at the same time. All right, so this is the list of objectives for this past week. I typed it up into the assignment. Thank you, Alex, for pointing out that I hadn't published it. That was the homework help. Ooh, okay, so that is my other attempts at that. So first of all, this we don't need. Let's examine the output. And the output can be understood from a combination of this. Let's see if I can simply get this. Not bad. Copy. And I guess I want a blank slide. New slide. Oh, and I had another idea. Paste. And let's take a look at this guy. And I want my snipping tool. And want new. Okay, here it is. Now, of course, I got to remember which one of these I'm using. There it is. And paste. Now, there are artifacts here, and Jaira and I have exactly the same thing, and obviously with very different apparatus. So I guess that's a function of the house voltage. But look at, though, here, we're taking a sine wave, and I suppose I'll use a different color. And we kind of expect Whoops. There it is. And we're not surprised now. And now before, with the single wave rectifier, notice there's a big gap here. And the big gap was because we're throwing away the negative lobe. With the full wave rectifier, we're keeping it. However, if we were merely making sure everything was positive, we would actually expect this to come to a sharp point. And it doesn't, because that is the diode drop. It does go to 0. Because we're measuring a V out. We don't have a reference. We don't know. We're grounding that point, right? So we're forcing this point here to be at ground. So we don't realize that it's not actually at ground because we have no way of knowing. And this is that region where one diode is, let's see if I can get a nice one, copy. And paste. So in the forward direction, then this diode is turning on. And so we wouldn't see anything till that diode is on. And then as it goes negative, then it's this diode here turning on. And so you're seeing that it's the time it takes for those to go from 0 to 0.6. And we could probably, I got to figure out a quick, you could probably convince yourself by measuring the time here, and you know you have a 60 hertz rate, so you could calculate the slew rate, but it's not a big deal, but it's you're seeing the effect of the diode drop. Because again, you don't really realize it with the rectifier until you carefully notice that it only goes to 9.4. If we were to do the clamp, then it would be in your face. This one is also kind of, but this one is more in your face, but you have a tendency to write it off to something you did wrong. But it's not. It's the diode drops you're seeing. Because you can't get a V out unless you have a current flowing. And so there's no current flowing while you're below the diode drop for V in. All right, so then the last part is about filtering. Now here's the same thing from previous time. So with filtering, so now I've added a capacitor. I added 0.1. I would encourage you to do this. Go ahead and add different capacitors. And notice what starts happening. You're starting to see the time constant of the capacitor when it's discharging. Why doesn't it affect the charging? Oh, right, of course. Because you have the resistor there, so you're measuring the voltage across the resistor. So it only affects the downward slope, where the capacitor then is discharging. So in a sense, what the capacitor is doing is it's providing you with this very quick charge and discharging battery to fill in those gaps. And then if you go to a bigger capacitor, notice 1 microfarad. Now the thing to notice is that I've set this up so the peak voltage is still there. So what I'm doing is I'm cutting off the lower voltage. One of the reasons to do this is if you go straight ahead and put in 15 microfarads, you're going to think you did something wrong because the output is going to look so radically different. So if you build it up a little bit at a time like this, like I did 0.1, 1, and then now I'd use 4.7. So he tells you about how to calculate this. So you can you get rid of it completely? I guess. I mean, I get it doesn't seem like it would be that expensive. We're going to eventually build power supplies, although that might be in semester 2. But in any event, you let's assume that you build yourself a power supply and you want so much ripple that you can tolerate because you don't want to have to spend too much. You want to build a power supply that is not too expensive, right? Or you want to provide one for the cheapskates and you want to provide one for the people who don't mind spending extra. And so remember that this thing we saw earlier when it was a smallish capacitor, notice that it's going to approach asymptotically. And just like when we did the integrator and differentiator, even an exponential curve at the very beginning is linear. And we're going to take advantage of that. So to figure out what exactly we want, first of all, we notice that the peak, and we deal with the amplitude, it's 10.4 volts. And we have a 15K resistor, and that gets us at peak 0.7 milliamps. Now, we didn't go through the derivation, but with a capacitor, the current is equal to the capacitance times the dV dt. So we can invert that to get the capacitance itself equals I times dt dV. And so we say to ourselves, okay, I want it to drop by 10%. I know the frequency here, just have to be a little careful because the period here, this delta t, is equal to 1/2 the 60 hertz period. Think about it. Is that right? No, it's wrong. Never mind. It's where it repeats, right? So, no, it is 1/2, of course, because this is a sine wave. And so this is 1/2 the wavelength, right? The full wavelength is when we were here. So remember, this is the negative lobe. This is the positive lobe, for example. So anyways, we want it to drop, and we specify 10%. So we want it to drop 1 volt in half a period in this case. And we know that the period of a 60 hertz is about 16.7. It's 16.6666 milliseconds. So I just say my delta t is 8 milliseconds. 10% of 10.4 is 1 volt between friends. And then I already know the current that I have there. And I figure out I want a 5.6 microfarad cap. So I tried to put a 4.7. And lo and behold, I measure now, is this peak to this difference, this peak to peak, what is it? And we want it to be 1/10 of the peak to peak from before. So that's what I would like to see in your logbooks, that you say, here's my rectifier output. Here's what happens when I add a 0.1, a 1. Here's my calculation, because you guys may have different output voltage. I have 10.4. Yours might be different. And I wanted to have a 10% ripple. And this is the value that I should have. And this is what I put in, and this is what I got. Now, there are we definitely have 10s and 20 microfarads. There's a few 4.7s. I would say is to scavenge the little plastic boxes that are out in the wild out there with you guys, and maybe you share them. Maybe you don't all get to that point at the same time. And you can add capacity. You have some 1 microfarads over here. I think there's actually some 4.7, the little yellow guys, right? So you can make combinations to tweak it up if you need a value that's a little different. Generally speaking, for these values, we use those black ones. Inside of the black ones are the rolled up paper and aluminum foil. Those ones are better for low frequencies like 60 hertz. But for the purpose of what we're doing, the little yellow guys will work just fine. Okay, so I'm going to stop this. And and let me just make sure there's nothing else here. No. And here I put 47 microfarads. And when you look at the output here on the right, you see almost no ripple whatsoever. I had to actually zoom in. That's why you see all these artifacts. And I set the sensitivity way up to see to open it up. So, anyways, that's that. Let me close.